students, welcome to Experimental Techniques and Material Characterizations, lecture number 18. I'm Dr. Pervez Ahmed. So this is the second part of the lectures on X-ray diffractions. So in this part, we will have a discussions on peaks and planes and the XRD patterns. So let's proceed towards today's lecture. So in XRD patterns, just like the one you can see here in this figure, this is belong to a single crystal specimens and a Bragg-Berthano diffractometer. So it will produce only one family of peaks and the diffractions pattern. So here you can see we have the peak, that is the first peak. You can see it here. It's at a 2 theta value of 20.6 degree, and the second peak is 29.3 degree to theta value. And similarly we have the other peak, and they are being tagged with respect to their corresponding plane. So let's first come towards the first peak, which is the main peak. It's at a value that is equal to 20.6 degree to theta. So what it mean? It means that the Bragg law fulfill for the 100 planes producing a diffractions pattern. So this is so the diffraction, this peak basically corresponds to the diffractions from 100 plane. Then we have another peak, and this peak is this correspond to 110 plane, and it is because of the diffractions from 110 planes. And what it mean? It mean that the 110 planes would diffract at 29.3 to theta degree. However, they are not properly aligned to produce a diffraction peak, and here we have the reasons. What is the reason? So here you can see the planes orientations, and also the perpendiculars to we have the perpendicular to those plane, and you can see that the perpendicular to the to this plane, it's being shown by the black dotted line. So it does not bisect the incidence. So it does not bisect the incident and diffracted beam. So here you can see this is this red one, this is the incident beam, and this is the diffracted beam. So the line, the perpendicular which bisect these two beams, it's different from the one that bisect these plane. So here we say that the condition is different. The peak physique is different from the one that we have from the 100 plane. And here is the reason. The reason is that we have the perpendicular to those plane does not bisect the incident and the diffracted beam. So only background is observed. So here we have we only observe the backgrounds. Then we have another example from 200 plane. We have a peak here, and the peak is at 42 degree to theta. So this peak is correspond to 200 planes, and be remember here, just like you can see it by yourself. So these planes are parallel to the 1 plane. So you can even check for yourself. So the orientation of these plane are just like similar to this plane. So the 200 plane are parallel to the 110 plane. Therefore, they also diffract for this crystal. So since the d spacing for the 200 is 1/2 the d spacing of 100, so they appear at 42 degree to theta. So that's the reason. You can see here the perpendicular to the incident and the diffracted beam, and also the perpendicular to the planes, they are lying the same plane. So here you can see also the natures of the peaks, so how it look like. You can also have a better look. You can observe what you have observed on the previous slide more clearly here in this particular slide. So here we have a polycrystalline sample. So for a polycrystalline sample, what we have, So for a polycrystalline sample, it should contain 1,000 of crystallites. Therefore, all the possible diffraction peak should be observed. I mean, you know the definition of a single crystal and you know the definition of the polycrystal. So in polycrystals, we say we can also call it a multicrystals. Or we have, I mean, we normally call that a material or a sample which contain many crystallite within the same sample, or we say many crystal within the same sample. For that, we should have multiple diffraction peak within the same XRD pattern. So a good example of that you can see it here. So you can clearly differentiate between the single crystal and the poly crystal. That I mean it's clearly visible to you. So here you can see that we have the major peak that is the 100 peak. So here you can see that it is again here for that particular value, just like we have in the previous crystal. So here you can see I mean the orientation of the plane. So here again you can see the perpendicular, the normal to the plane is exactly is the same. I mean they're lying in same directions, just like I mean the normal to the plane, and also the normal to the incidence and the diffracted beam, they're lying in the same. So for every set of planes, there will be a small percentage of the crystallite that are properly oriented to diffract. So what it means? It means that the plane, I mean that I already mentioned, the plane perpendicular bisect the incident and the diffracted beam. I mean both of these bisects, they are I mean perpendicular. So that's just why you can see it here. So in this condition, I mean we have the 100 plane. So here I mean the peak the is being diffracted from this side of the uh, plane. So here you can see the peak orientation, the plane, the X-ray which diffracted from the plane is almost the same, just like we have for the 200 plane. So here you can see that. I mean the plane, the orientation of the planes, they're almost, I mean so they are the same exactly. So only you can see that how the beams they come and they diffract. So here if we check for this one, so here the orientation is different. So the basic assumption of the powder diffraction are that for every set of planes, there is an equal number of the crystallites that will diffract, and that there is a statistically relevant number of the crystallite. I mean, it's not just the one or two. So accordingly, we will have, the peak, the width, and the peak intensity. Powder diffractions is more openly named polycrystalline diffractions. I mean, we rarely have a single crystal in that, uh, and some I mean, sample can be powdered, center pellets, coating on a substrate. I mean, it's engine block, etc. So that is the most common. I mean, you can say conception, or you can say knowledge about the X-ray diffractions. That powder diffractions is more properly named polycrystalline diffractions. And the reason I mentioned that very rarely we have a single crystal, and whenever we have a single crystal, so we will have a special arrangement of the diffractometer for analyzing that single crystals. And if the crystallite, I mean, you know that we have the orientations for the crystal samples. I mean, when we put the sample inside the machines, you know that in majority of the X-ray diffractor machines, we have a fixed X-ray source, and normally we have the specimens which rotate. So if the crystallites are randomly oriented, and there are enough of them, then they will produce a continuous Debye cone. I mean, just like you see here. I mean, let's suppose we say this is the powder specimens, and we have the X-ray source from here, and we strike that X-ray on the specimens, and now we are saying that if we have a sample and that sample contains many crystallites, and if we are saying that these if inside this sample, if all the crystallites they are randomly oriented and there are enough of them, I mean if we have inside this sample, if we have many small crystallite, and along with that if these crystallites are randomly oriented, so then they will produce a continuous Debye cone. So the Debye cone is just like the one you can see it here. So this is a particular conditions for randomly oriented crystallite. So if we have randomly oriented many crystallite inside our sample, so they will produce a continuous Debye cone. So I mean you can see and you can observe for yourself. And in a linear diffraction patterns, unlike these conditions, in a linear diffraction pattern, the detector scans through an arc that intersect each Debye cone at a single point, uh, that giving the appearance of a bisect diffraction peak. A good example of which you can see it here. So this is the example for that. I mean they I mean we have two conditions, and first condition we say that if the crystallite are randomly oriented and there are enough of them, so then they will produce a continuous Debye cone. So here is the continuous Debye cone. And now we have another conditions, that is in a linear diffraction patterns, the detector scans through an arc that you can see or you can check for yourself, that intersect each Debye cone at a single point. I mean you can see it here, thus given the appearance of a discrete diffraction peak. So you can see it here. Along with that, we also have area diffractions. So area diffraction allow us to image a complete or incomplete Debye diffraction ring. So here you can see we have example of two materials. That is the first one, for example, this one is a polycrystalline thin film on a single crystal substrate, and this one is a mixture of fine and coarse grain and a metallic alloy. So this is a good example of area diffractions. I mean that allow us to image complete or incomplete Debye diffraction ring. So conventional linear diffraction patterns would miss information about a single crystal or coarse grain materials. And we also have linear diffraction scans that have better resolution and less noise. So here, I mean, this is the example of linear diffraction scans. And we remember linear diffraction scans have better resolution and less noise. And most oftenly, we have linear diffraction scans. I mean, normally you people might have seen most of your research papers that we have this kind of the XRD pattern. This is called linear diffraction scans that have better resolution. So here you can see that how much the resolution, how better the resolutions we have depend upon your sample, depend upon the nature of your sample, and also the type of the software you use to draw these I mean results after the analysis. Diffraction patterns are best reported using the d-spacing and relative intensity rather than true theta and absolute intensity. So the peak position as 2 theta depends on the instrumental characteristic such as the wavelength, whereas the peak position as d-spacing is an intrinsic instrument and dependent material property. So a Bragg lag is used to convert the observed true theta position to d-spacing. And I mean this is the most important things we should keep in mind. that whenever we try to run your sample inside the machine, so you should keep in mind the relation between the two theta, and also the wavelength of the radiation, the wavelength of the X-ray which you use to characterize your sample. So the peak positions here, you should keep in mind about, you should take some special care about this, that the peak positions uh, which we take as 2 theta, it depends on instrumental characteristic such as wavelength, and the peak position as d-spacing is intrinsic instrument and dependent materials property. So we have 2 theta that depend on the instrumental characteristic, and along with that we have the d-spacing. So the d-spacing is the intrinsic property, uh, and it not depend upon the it's not dependent upon the instrument. So brake law is used to convert the observed 2 theta positions to uh, the d spacing. So the absolute, along with that, the absolute intensity, that is the number of X-ray observed and a given peak, can vary due to instrumental and experimental parameters. That is, the relative intensity of the diffraction peak should be instrument independent. So to calculate the relative intensity, uh, divide the absolute intensity of every peak by the absolute intensity of the most intense peak, and then convert it to a percentage. So the most intense peak of a phase is therefore always called the 100% peak. So that you can take from the XRD pattern which you people have observed on the previous slide. The good example of that. The high intensity peak, we always take it as 100%, and the rest of the intensities we can calculate accordingly. Just like we mentioned in this slide. That is the largest peak, just like the one you can see it here. You can check it more clearly. uh, here, this is the largest peak, so we take the intensity as 100%, and then with respect to this peak, we take the intensity and percentage of this peak, and also this and this. These are called the relative intensity with respect to this one. This one, the highest peak, we take it as 100%, and the others, they are being taken with respect to this first one. That's why they are called relative intensity with respect to the first one. So peak area are much more reliable than peak height as a measure of intensity. So this is also an important point. One, the researchers should focus on that peak areas are much more reliable than peak intensity as a measure of uh, intensity. Powder diffraction data consists of a record of photon intensity versus detector angle, that is 2 theta. So here you can see we have raw data. So the positions is normally, you know that the position is in measure and 2 theta degree, and the intensity normally we take as counts. So here you can see that these are the 2 theta values, and these are the counts value. It's is the intensity. So diffractions data can be reduced to a list of peak positions and the intensity, just like you can see it here. And this corresponds to this 2 theta position and intensity. If you put it in any relevant software, so it gave you the XRD pattern like the one you can see it here. So these positions and intensity corresponds to this XRD patterns. So each d-spacing corresponds to a family of the atomic planes that we denote by HKL. So here you can see it here. So all the d-spacings that you can see it here, and it's not on the in the angstrom, they corresponds to different planes with the relative intensity. You can see, you can check it by yourself. So individual plane I mean the individual plane we cannot be resolved. So this is the limitation of the powder diffractions versus single crystals diffractions. So that's all we have for this lecture. Thanks for watching, but stay tuned for the next lecture because in next lecture we will deal with the XRD peak analysis. So stay tuned. Till then, bye bye.